Hello, so welcome to today's lesson, which is composition of the atmosphere. So the atmosphere is a mixture of gases, and they are held in place by gravity. So the force of the Earth's gravity is strong enough to retain it for like a layer around the Earth. So what is the atmosphere made out of? Now, there are a number of important gases that you need to be aware of. So the gases that we're looking at are nitrogen, oxygen, carbon dioxide, rare gases, which includes things like methane and xenon, and argon and krypton and all these sort of inert gases, and then ozone as the last one we've got here. So nitrogen makes up the majority of the Earth's atmosphere, so it's 78%, and it's an inert gas, so it's largely found in the atmosphere. Okay, there are a number of processes that remove it from the atmosphere, things like nitrogen fixing bacteria, remove it from this like source, and put it into a sink, and you've got denitrifying bacteria that put it back into the sort of atmosphere. Okay. Next one, then we have oxygen, which is 21%. So this comes from things like photosynthesis, from photosynthesizing plants and organisms, those photoautotrophs, and then it's removed from the atmosphere via things like aerobic respiration or chemical processes like oxidation. Carbon dioxide makes up a really small proportion of the Earth's atmosphere, so 0.04. An important way that this is added into the atmosphere is aerobic respiration, where complex organic chemicals are respired in the presence of oxygen, producing carbon dioxide. Other sources are things like volcanoes, which release CO2 back into the atmosphere that's been stored as rocks in a form of chemical reaction or combustion. And then a sink is going to be photosynthesis, where it's removed by plants or algae or photosynthetic, those photoautotrophs. And you've also got things like dissolution into the oceans, so it will dissolve into oceans. Rare gases are a mixture of different things. So if we look at things like neon or krypton or something like that, this is totally inert and just sort of floats around in the atmosphere, and that's a result of radioactive decay in the Earth's crust. Things like methane, however, are carbon-containing compound, and that is from anaerobic respiration, things like decay in swamps. And the sink is methanogenic bacteria, which means bacteria that eat methane. And then the last one is ozone, and this makes up a tiny, tiny proportion of our atmosphere. So let's make sure I get the right number of zeros. Okay, so a tiny percentage of our atmosphere, most of it's concentrated in the upper atmosphere. And this is from the use of, or the breakdown of oxygen in the presence of UV radiation to produce ozone. Okay, and it's broken down in the same way. So it will also, in the presence of UV, decay back into oxygen. So it's like a dynamic balance. So these gases have remained at a constant or relatively constant concentration for a very long time because they are in dynamic equilibrium. If I can get it to move down for me. Oh, that's not going to do it, is it? So a dynamic equilibrium is where two processes are in balance. So the and this keeps it stable or the same over the long term. So even though we get fluctuations in concentrations, they will average out over a long time. So an example would be aerobic respiration versus photosynthesis. And this is for the gas carbon dioxide. So aerobic respiration releases CO2 into the atmosphere and photosynthesis removes it. And we can see this in action because if you take very accurate measurements of CO2 over the daytime and you go to places where there is not significant sources of human CO2 emissions, you can see naturally the global concentration of CO2 in the early hours and at night actually increases to a peak at about 6 o'clock in the morning. Okay, and then it will decrease as sunlight strikes the majority of the northern hemisphere. So during the daytime, it's northern hemisphere because it's got lots of plants on it. And then we see the amount of CO2 actually decreases until it reaches a low point at about 2 o'clock in the afternoon. And then CO2 concentrations will increase again as the day continues and the amount of light decreases. So this is the fluctuations are controlled by light on a daily cycle. So the more light you have, the more photosynthesis. So up here, we've got lots of respiration, but no photosynthesis. because it's dark. Now we have photosynthesis that is happening at a greater rate than respiration, which you'd assume continues at the same rate. And then as the day grows old and the sun starts to set, the amount of photosynthesis decreases. And the amount of respiration remains the same. If it changes colour for me, that is. There we go. We can also see this on an annual cycle. So during the early part of the year, CO2 concentrations are relatively low, but they will increase as the winter continues before reaching a high point around about April, May time. It will then decrease until we get to September before starting to increase again over the autumn and start of the winter. Okay, so these are annual fluctuations. And this is due to the Earth's tilt changing insolation on the northern hemisphere. This is because the northern hemisphere has the most land mass. So seasonal changes there have a bigger impact. So we have respiration actually increasing because of decomposition over the winter of things like leaf fall and stuff like that. So respiration is greater than photosynthesis. Until it reaches that peak in April, and then we find that the increasing level of light available due to the seasons in the northern hemisphere means that photosynthesis increases, and the amount of decomposition and things like that means that respiration either remains the same or decreases slightly. And then we find that respiration starts to kick up again a little bit in the autumn as all the leaves fall, and then photosynthesis declines as autumn and winter kicks in. So we can see this dynamic change. If we measure the average CO2 concentration over the entire year though, and over several years, we'll find that it remains relatively stable.